Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome you all in lecture number 6, okay? In lecture number 7, sorry. This is basically lecture number 7. Clear? So in this lecture inshallah we will discuss about the design of the beam, okay? So before we going toward the design, you must understand these coefficients because we are using these coefficients, okay? Now you see in this diagram, I taken this diagram from Nelson, okay, 10th edition. Now the first coefficients are basically for what condition? The discontinuous, and remember we have only two spans here. These are applicable for, okay, more than two spans, remember, discontinuous and unrestrained, okay? When your continuous they were discontinuous and are unrestrained means that the beam is basically simply supported. It just placed over a wall, okay, like in our case. In our case basically you see here that the bars are just only placed over the walls. There is no L beam, no L beam, or you can say no columns, etc. Okay, so that's why basically the edges are unrestrained. Clear? The edges are unrestrained. Let me show you that sometime we basically provide, you see here that there is no L beam at the walls and no column, okay? We just place the slab over these walls. So this means that our edge, basically the beam is right here. You see the beam is right here. This is the beam. Clear? Now the beam here basically there is no column to provide the end to the end of the beam. Basically they are just placed over the wall. So here we have wall and the beam is just placed, okay? No fixed support, okay? So this is a simply support. So this is how we call unrestrained. Clear? This is how we call unrestrained. So let me show you, if you have an unrestrained, so then the moment will be 0. Theoretically the moment will be 0, and for positive movement you have to use this coefficient, and for the first the movement at the first interior support at the exterior face, this coefficient, and for next this one, and so on. If you are providing L beam, remember sometime we provide L beam, okay? So if you have an L beam means you fix the edge, so that why your coefficient will be 1/24, and for mid span it will be 114. And if you provide column to the column edge, okay, so then the coefficient will be 116. Here you have negative moment, 114, and so on. Remember, this is very important. Most of the people do not understand these coefficients, remember. And the same condition, but here you have two spans, okay? Discontinued edge, unrestrained, spanner, and column. And these are for slabs, and here they have slabs with spans not exceeding 10 feet. But remember, you can also use these coefficients more than 10 feet span, okay? And these are also, and here you see this is negative moment, okay? Maximum movement diagrams and movement envelopes, maximum positive movement, remember. So these coefficients vary. Our case basically the first one, because the ends are unrestrained, so we will use this 0, 111, 110, and 111. We will use these cases, remember, these coefficients, because our ends of our beam is unrestrained. Clear? So these are the coefficients which is explained here, okay? When your ends are restrained, unrestrained, okay? And for shear basically these coefficients works for movements. For shear, you see shear in end members at first interior support. Remember, this is very important. This is first interior support, and at the face, at the first interior support at exterior face, the shear will be here is 1 point, you can say 15% more than the shear will be at this face. Only for this. And here again the same shear, that is you can say WU LN divided by 2. So here this is the only point where the shear is 15% more. Similarly for the exterior, this is my exterior panel, or this is my end panel, and this is my interior panel. Okay, so I will explain. Okay, so here we have, and this is the final detailing diagram, remember, that we basically discussed in lecture number 6. Okay, and basically you see this is the extra bar which is provided at the in panel A at the support. Okay, at the column, at the beam, sorry, beam. So beam is this end of the panel A is continuous with the panel C, so that's why the top bars are shown here. And similarly you have to provide extra bar here or bent up bar here, and you see the torsion reinforcement, at this end as well, and the other things are also self-explanatory. Okay, now we start the design of beam. To design a beam, the first, you see the moment coefficients. Here basically I am using 0, 111, 110, 111. I find out the clear spacing. Remember, this is my panel B, and remember this is my beam 1, this is my B1. So here basically I designate the beam not accurately. This is my beam 2, remember, that is simply supported beam. I will design it in later. Okay, so this is my simply support, this is B2, and this beam basically which is provided here, this is actually B1. One here we have 4 beams, remember, one here in this way and one here this way. Okay, so and one here. Okay, so these 4 beams are symmetrical, and remember the width of these beams are 12 inch. Okay, and the length, this is panel A, so this is 18.93, then again 19 feet, and then again 18.93. so this must be, you must understand. Okay, you must understand that how these bars are placed and how to basically maintain the spacing. Clear? So let me show you. Here we have, so you see 18.93, then 19, then 18.93. the size of the column is basically assumed that it is 12 inches or 1 feet, and remember the beam width is also assumed that is 12 inches. Okay, now the tricky part of this design of beam is your H minimum, the determination of your H minimum. So basically to find out the actual value of H minimum, let me show you, we use basically 3 criteria, and let me show you those criteria, how I basically find out these widths. Okay, so I think so I do not share that calculation here, but let me show you here. Okay, let me show you here that whether is that calculation. It is very important calculation, and you must understand that calculation, that how we can find out the depth of the beam. Okay, so very important calculation, I think so, this one. Okay, yes, so you see here selection of depth of beam D. Now we have draw the diagram. You see this is slab portion and this is beam rib, and we have to determine this effective depth. Okay, now you see that we will using three criteria to find out the depth. Remember, it's very important to find the actual depth. Remember, it will works in serviceability, it will works in ductility, as well as it will works in shear. Okay, so these criteria control the depth of the beam. Remember, the thumb rule is that if you have 20 feet span, you have to provide 20 inches, 1 inch for each feet. Okay, 20 inch minimum depth of the beam. This is for serviceability criteria. So let us check it. H minimum is equal to, in this case, basically L divided by 18.5 times 12. So this 18.5 is now our coefficient. Remember, for simply supported span, it is L by 20, but for continuous, this is L by 18.5. Remember, multiply by 12. I will share inshallah these coefficient. Okay, times 12. So L is 18.9375. Okay, we have two spans. Remember, one is 19 and one is 18.93. So you can check it for both spans and you select the maximum one. So 12.2 inches is now my depth of the beam from deflection criteria. Now I am checking from ductility criteria. Remember, you have to provide such a depth of the beam that the steel chick which we make, basically rho provided should be greater than rho minimum, and should be less than rho max. Or you can say AS provided should be greater than AS minimum but less than AS max. So if you provide lower depth, okay, then your steel area is exceeding from maximum steel. Okay, and if you are providing maximum depth, so what will happen? Your steel area is increasing, is becoming less than the minimum reinforcement. So that's why we have two limits, lower limit and upper limit. Upper limit is my maximum reinforcement and lower limit is my is for my minimum reinforcement. Okay, so here you see our rho max. Okay, how to calculate rho max? Basically here I am using 0.0214 already, but this is the formula which can be used. Remember, if you are using 0.005, you must make sure that your pi value will be 0.9 and you will check that value, that whether it will 0.9 or not. So how we can check it? I basically explain all these things available on my channel, basically, that how you can check the design of doubly reinforced beam. I think so. The design of doubly reinforced beam, which is available in my PRC 1 and PRC 2 course. The design of doubly reinforced, bilkul. Basically I explain the whole procedure in that videos. Okay, that how you can check that whether my value is 0.005 or not. Okay, and similarly now you see here okay, you see here rho max. My FC frame is 4 KSI, FY 60 KSI, and when I plugged all the values I got 0.02 or 0.01 at something. Okay, so I am using 0.0214. okay, now next we have a formula and my rho minimum is 0.0033 from these two formulas, and you know these two formulas. Okay, now to find out the D minimum or the depth of the beam, BWDM square equals to MU divided by pi rho provided into Fy into 1 minus 0.59 rho provided Fy divided by FC prime. This is the formula. From there we will got the D minimum. So let's say here we will use rho provided. First of all, equating rho provided with the rho max, and then we will equating rho provided with the rho minimum. So we got two depth values. Okay, this is important. We fix the beam width, that is 12 inches. Now the problem is that we have to calculate MU. Okay, MU, we need MU, and you see here MU. Now calculating MU on the basis of slab weight and then later include the beam self weight, because whenever we are designing a beam, we include the self weight of the beam. So as we don't fix yet the depth of the beam, so that's why we don't know about the depth of the beam. So that's why here we will assume basically the self weight of the beam. Now we need to find out the self weight of the weight of the slab which is coming towards the beam. So this is 1.04 times 2. This is 1.04 is the weight, is the load basically which is coming from the slab to the beam. And I will explain this 1.04 in my coming lecture, I think in lecture number 8 inshallah. And I will completely explain this, that how the load is basically distributed to the beam. Okay, so you don't need to be confused in this 1.04. And this 2 is basically nothing. It shows that the load is coming from two direction. If I show you here, inshallah in next lecture I will explain these slides, okay, in very depth detail. You see the tributary area for this beam, and you see this is my tributary area. So the load which is coming from this tributary area is 1.04. So from where this 1.04 comes out, I will explain this, okay. I will thoroughly explain that from where this 1.04 comes out, okay. And here you see 1.04, which is load distribution. In next lecture inshallah I will explain it, okay. Now you see here that 1.04 is from one side, so multiplied by 2, so for counting for both sides, and 0.2185 is the slab portion weight which is just provided over the beam width. Remember, it's very important. For example, if I have a beam over here, so the next important thing is that the slab portion which is just above the beam. So you know that the width of this slab is 1 feet, because the width of the beam is 1 feet. So that's why and its thickness is 5.5 inches, okay. So the weight of this slab portion which is just above present at the top of the beam is 0.2185, because we already calculate this weight. At the slab weight is basically which is coming toward the beam, toward the per square foot weight of the beam, of the slab, sorry, per square foot WU basically, that is 0.2185, okay. Keep per square foot, remember, per square feet, okay. So you must remember, okay, you must remember this weight, okay. Now adding these two, you got this one, and now you see that the rest of the calculation, that is 110 times WU ln square. 110 is that coefficient. I select the larger value, okay, to give me the maximum moment, okay, to find out the larger depth, okay. So that's why I'm using a conservative approach, not 116, 111. I use the larger one. Ln square, we have two values, 18.93 and 19. I using 19 because to give me larger moment, conservative approach. And I plug the value, I got the moment. Now add in 10% for the beam self weight. So finally I got the moment 1096 kg per feet. Okay, this is my final moment. Now to find out the depth, I just equate rho provided with the rho max, keeping the value of moment this one, and I calculate depth d is equal to 9.87. This is very important depth, remember. This depth, what it mean basically, remember this is the depth which provides basically the lower boundary of our beam depth, that we should not decrease the beam depth from this 9.87. If we decrease the beam depth, provided depth of the beam from this 9.874, this will shows that your steel area of steel should be maximum than the maximum steel limit, okay. It will crosses then that limit, clear. So that's why this is the minimum, or you can say the lower boundary. The next is the upper boundary, and here I am equating rho provided with a rho minimum and plug this value for the same moment, and do the calculation, you got 22.97. This is my upper boundary. Now I can't increase the depth of the beam from 22.97. If I increase the depth of the beam from 22.97, then my steel area will become a smaller value. You can say my steel provided should be less than my steel minimum. Okay, so this is the check. You see, row provided or depth provided, the beam depth should be greater than this one but should be less than this one. If we use this check, then remember, you will definitely pass that check. That is ductility check. Okay, so this is the beauty of this calculation, remember. And the next and the final one is the shear criteria. We fix the beam depth from shear criteria as well. And to fix the beam from shear criteria, ACI provide us this pi BC, the strength of concrete, 6 pi FC prime BWD. From here we can find out D. We have BW, we have pi value 0.7 FC prime, and pi VC is basically, we equate this with VU, and VU is equal to 1.15 WU ln divided by 2, and I explained 1.15, this is a coefficient. And we select, we have basically at only one region, that is the first interior support at the exterior face, this shear is possible, and all other regions the shear is WU ln divided by 2. I will explain this, okay, in my coming lecture when I was designing basically the shear reinforcement. Okay, so we calculate VU from here. The WU will be the same. Okay, I using ln 19 because to get a higher value. The same calculation for WU you see here, adding 10% for the self weight of the beam. Okay, the same loading, and here when I plug the value of WU in this formula, I got 27.62. This is my design shear right now. And now equating that VU with pi VC and finding out the depth, that is 8.1 inch. So this suggests that to control shear, remember, we have to control shear, because in if the shear value become more than that 6 phi or 8 phi, I think so. So what we have to revise the beam design. Okay, we have to revise because practically it is impossible. The shear amount is more. Okay, so then we have to we try to minimize the shear lesser than this value. Okay, this is very important, and this is the beauty. Okay, now finally you see from deflection criteria we have this depth. From ductility criteria we have these two limits, and from shear criteria we have this one. So we can't use this criteria because this is rejected. This criteria is rejected. Okay, this criteria is now rejected, and we have searched this criteria. 12.2 coming within this limit. So finally ductility criteria governs, and almost ductility criteria governs. Okay, so we have to choose the depth in between these two values, okay. Remember what they say. Remember, most of time ductility criteria governs. Let us use D is equal to 15 inch using effective cover to the center of the bar 3 inch. Our required H is 18 inches. Okay, so this is how we can fix the depth of the beam, and this is the way that how you can efficiently find the depth of the beam. Okay, so here you see my H is basically you see my H is 18 inch. I write here. Okay, so although I don't use those tricks, but this is for your general knowledge. Remember, this is for your general knowledge. And if you find out the depth from your deflection criteria, that is 12.2 inches, so increase this depth by amount of 8, 9, 10 inches. Okay, increase depth, so it will definitely then work. Okay, the depth is effective depth is fixed. Now the slab load calculation, this is important. Remember that we have two approaches. Okay, either I will show you theoretical way, and then I will show you the graphical way, how we can calculate graphically these loading. So panel A, basically you see our WU, 0.218 already been in the second lecture we calculate 0.2185. okay. Now if you want to find out your panel weight, you have to just multiply your factor load with the area of the room or panel. Clear? So this is WU 0.2185 and this is your panel A area. Clear? This is 78 kip total load. Okay, remember if you have a panel, this one, so the total load of that panel A is 78 kip. Okay, 78 kip. This is important to memorize. Okay, now remember these coefficients. Okay, these are the coefficients which we basically select from tables, and I explain basically these coefficients. If you watch my channel playlist here, I explain these coefficients thoroughly, and here I don't want to waste my time. Okay, but if I got the time here, I think so. Yeah, here where are those diagrams, where are those tables basically from where we select basically these WUs. Okay, so here you see beams. Okay, and where is that? This one, this is the table. Okay, you have to write down the panels, then beam IDs B1, B2, B3, your length, but remember this is the length of the beam. Okay, the span length, and this is the transverse span length. Okay, transverse span length, because if this is my, let's say is my beam 1. Okay, so its length is 25 feet, but it's the width of the supported panel. Okay, this is BS, this is transverse span. Okay, half of that panel and half of that panel. This beam will support half of that panel and half of that panel. Similarly, half of this panel, half of this panel. So that's why it's supported width of the width which it support is 10 feet. Remember, this is 20 feet and this is 20 feet. So half that 20 by 2 and 20 by 2, so 10 feet. Okay, and this WA is from table. Okay, this WA is from table, remember, and the table is right here, I think so. This one, selection of coefficient for given example. Yes, this is the table. Okay, and I explain this table because in this case my M value is 0.8, and the case you have to select the case and then find the coefficient. So basically these coefficients will work. Okay, so you need to use this table and search the values, and I share those values. What are the amount of those coefficients? Okay, I already write down here. Okay, these are the coefficients. So these are the coefficients which I basically select from that table. So I don't want to waste my time. If you are interested to learn these things, so please watch these lectures. 2 slab analysis available on my channel. You will understand how to use those coefficients. Okay, so here I am using the same coefficient. Okay, and you see the total load is 78. Now the 29% will be distributed in shorter direction and 71% will be distributed in longer direction, and 22.6 kip, 55.38 kip. Okay, this is the cross section of the beam. Basically 12.5 and 3 inches effective cover, and remember the total effective depth is this one, that is D, and D is 15 inch. Okay, 15 inch. Remember the overall is 18 inch. Now for panel B, you find out the total load, that is 78.4 kip, and as panel B is square, so that's why equal distribution of loading. Okay, equal coefficient 0.5, because in square panel the load distribution is same to the 4 sides. Similarly, panel C is also square, so you find out the total weight and you have to multiply, because this is square panel, and in square panel basically the load is equally distributed to all beams. Okay, on 4 sides. But as panel A is not a square panel, so that's why different 29% in one direction and 71% in another direction. Clear? And finally the beam rib weight. Okay, you see there is the rib is basically 12.5, I think so. They use 12.5, but I think so 15. Total overall is 18 inch. So this is 18, and you subtract the slab, this portion, so that is 5.5. so subtracting 5.5 from 18, you got the beam rib. Okay, and multiply it with 12. So you see the width of the beam. Now you find the area of this rib. Once you got the area, you have to divide it by 144 to convert it in foot square, and multiply with density, multiply with 1.4, that is factor, and the okay, this is factor, and now 1.4 is factor, and you also need to multiply it with linear feet, because remember, if you have a beam like in this direction, let's say this is 3D view, so we are considering one linear foot length of the beam, not for the whole beam. We are just only consider 1 foot length of the beam. Okay, so that's why you have to multiply this one with a 1 feet. So here you have square feet, okay, and here you have foot cube. So that's why things will cutting down, and you got kip per feet. Okay, so this is the way how you can do the calculation. Clear? Slab above the beam, I already explained this point. This slab, okay, this slab. So the weight of this slab portion is how much? Is 0.2185, and I already explained this point when I was calculating the depth of the beam. Okay, so this is the weight. This is this weight which is just over the above the beam rib, and this is the weight of the beam rib. Now total load on beam B1 W 1.04 times 1.04. Now from where this 1.04 comes out? So in my next lecture, inshallah, I will show you graphically, but here you see here 39, because on beam 1, okay, on beam 1 you see here, this is my beam 1, this one, this is my beam 1. So load is coming from panel B, panel C, and then again from panel B. Now the panel B weight is 39.2 kip. Okay, so 39.2 kip, you see WA and WB. Now this is important to understand. Remember, this is very important to understand. Now you see this panel, that 39 basically in this direction, in both direction, okay, and similarly 39. Clear? Now we need to divide 39 by 2, because half toward that beam and half toward this side. Clear? So that's why 39.2 divided by 2. Okay, so it will give you in one direction. Then you see this, if I divide this panel in half portion, you see this is my half portion weight. Now this is my half portion weight. If I divide, this is 19 point something kip. This is a half portion weight. Now I need to divide this by, because this is aerial load, I need to convert this load into one strip. Okay, 1 foot strip. Okay, so that's why I divide this by the transverse weight, that is 18.9375. okay, so if I divide this, I got 1.04, I think so. This is the way that how we can do this calculation. Okay, how we can got 1.04, right, this one. Okay, if you divide the calculation, let me check out. For example, let me show you in panel. Yes, I also will show you 39.2, I think so. Where it is 39.44. So 39.44 divided by 2, that is give me 19.72, and 19.72 is divided by 18.9375, it will give me 1.04. okay, so 1.04 I got. Clear? So this is the way that this is basically nothing, 39.44